So we came to chapter 4, circuit analysis methods. So in chapter 3, what we have done, we said for any resistive circuit we can write two any equations which has got two any unknowns as well in it, and then we can find a unique solution for those. Now in this chapter we are going to introduce some new analysis methods which is simpler than this one. What do we mean by saying simpler? Can we do it with a less number of, so by the solution of less number of equations? So let's start from the problem first. What is the problem? In order to analyze a circuit which has any elements, any equations with any unknowns needs to be solved. That's chapter 3. We've done it. Now question, could it be possible to solve or analyze a circuit with less than any number of equations? Answer, yes, but unknowns should also be reduced as many as equations. So when you reduce the number of equations, in order to find a unique solution, you've got to also reduce the number of variables. If the number of unknown variables, and the number of equations are equal, then you have a unique solution. So that means we're going to introduce some new variables in order to solve that problem. There are two alternatives to this one, which will be introducing new variables. These are mesh currents, one of them. The other is the node voltages. Each of them means a new method. So if we come to the whole page once again, so we said there are two alternatives for that one. One of them is the mesh current method, the other one is the node voltage method, and we're going to mention the conclusions as well from those two methods. So the first video is going to be related directly to this mesh current method, which is this video. Let's go inside. Circuit analysis by mesh current method. New variable, as we said, is mesh current. Assume that for each mesh there is a current such that each element's current can be written in terms of mesh currents. Now we are saying, as we already said, there are loops and meshes. We said meshes are special loops which do not have any other loop inside. And then we said for the meshes, all the Kirchhoff voltage law equations that you write for the meshes, they are independent. So we are now adding a new variable to this mesh. We are saying assume that each mesh has a current, which is called mesh current. Then if we say that, if we find all the elements current in terms of mesh currents, that tells us we reduce the unknown currents to the unknown mesh currents. Mesh current is less than the NE, of course. NE is the number of currents. For each element there is a current. So NE number is going to reduce the mesh number, which is less. How we are going to do it? Is it possible to do it? Let's come to the next frame. How to write an element's current in terms of mesh currents. So here you are. If an element is in one mesh only, element A in the figure. So we are talking about this element A here. So this element A is in the mesh 1 only, this mesh. But if we talk about the element B, that one is the common element in mesh 1 and mesh 2 as well. So these are two different elements according to where they belong to. So let's consider this first one now. There is only one mesh current, this element is included in only one mesh, and this mesh has got that mesh current. This is the one that we have shown here. So this mesh current is direction, mesh current's direction is the same as the element current direction. So that means both of them the same direction. So we can say that this element, IA element current, must be equal to the mesh current because there is no any other mesh current on it. So for these specific elements, we told how we are going to write this element current in terms of mesh currents. Mesh current, not S, not included there. So look at the other one. That is the other side. But just one thing I have forgotten. So if the direction of the mesh current and the element current is the same, so these are equal. If it were opposite direction, assume that this mesh current is that way, then it was going to be minus. It is explained here. So another case could be an element which is shared by mesh 1 and mesh 2. This is element B here. How we are going to write the mesh current for this? It seems easy, a superposition that we are using here. If the element current is the same as mesh current 2 here, direction, so mesh current 2, which is IC2 here, is going to have a plus sign. If you look at the other mesh current, is the opposite direction to the B element's current. So this mesh current goes up and element current goes down. So this is the opposite direction. So this mesh current is going to have a negative sign in it. So add those up, it becomes EC2 minus EC1 is this element current. So if we use this rule, we can say that once you know the mesh currents, then you can find out all the elements currents. That is the title of it. Have to write an elements current in terms of mesh currents. So it is easy that we could do that. So let's come to the method now. Mesh current method. There are three steps that we've got to follow to end up what we wanted to do. Step 1. Write independent Kirchhoff law equations. You know the Kirchhoff law equations, independent ones are those which are written for the meshes. So if we've got NE minus ND plus 1 equations like that, number of KVL equations, NE minus ND plus 1, the unknowns seen in these equations are the element voltages, which are any number of them in these equations. So the next step, it says using the elements definition relations, substitute elements voltages for element currents. So if you consider a resistor now, resistor voltage is going to be seen in this Kirchhoff voltage law equation. So it says use the definition relation, then you can replace these resistor voltages with the resistor currents. What it means, you're going to write V equal to R times I, so that means you transfer the voltage to the current of this element. So we are transferring voltages to currents, then the equations, the number of equations is not going to change, but since we changes voltages to currents, so the unknowns are going to be element currents. In the first step it was element voltages, it is now element currents. For the other elements, what we are going to do is a bit critical, and I will be explaining in that step 2 here. So just remind, we could explain it later on for the other elements apart from the resistors. Now the third step, so at this stage what we have, NE minus ND plus 1 equations. In these equations I have got element currents, NE element currents. Step 3, so the elements currents, we already show here that all the elements currents can be written in terms of mesh currents. We will be doing this operation on step 3. Substitute element currents for the mesh currents. If we do so, the number of equation is going to be Ne minus Nd plus 1. Since the element currents replaced with the mesh currents, the number of mesh currents is the same as the meshes, so the number of equations is going to be the same as unknowns, which are mesh currents. So equations, unknowns, they are the same, so we're going to find a unique solution. That unique solution means find all the mesh currents here. Once you found the mesh currents, then you could use all the elements current. From the definition relation, you can find all the elements voltages. Now in step 2, we've got to pay an additional attention. Why is that? It says in step 2, if an element voltage cannot be substituted for its current. So there are some cases that you cannot do that. So for the resistors, we could do it. We could also do it dependent voltage sources, because dependent voltage sources has a definition relation, so you could use that definition relation. But we cannot use the definition relation for some of the elements. These elements are independent current source voltage and dependent current sources. Here current controlled current source voltage, and here voltage controlled current sources voltage. So if the elements voltages that we have seen in step 2 includes these elements, then I cannot use the definition relation of these elements to transfer these voltages to current. Why is that? Because I know that this independent source and this dependent voltage sources is not included in their definition relation. For example, independent current source definition relation is the current equal a given function. Voltage is not known. This voltage determined by the circuit it is connected to. So in the definition relation, we cannot see that V. So we cannot apply this, the first step, the first synthesis, what's said here. And it is also true for these dependent current sources voltages as well. We cannot use the definition relation to transfer it to the currents. So we are going to keep these element voltages as it is in step 2. We cannot change, we cannot replace those variables. Now the conclusion is that, so our unknowns are going to be the mesh currents, we know that, and if we have these type of elements, this type, that tree type, any of them, any number of could be, if you've got this type of elements, these type elements voltages are going to be the same as unknowns at that step. So what does this mean? For each this type of voltages, we have got to write an additional equation. This equation called supplementary equations. How we are going to write it? Is explained here. We are going to use the definition relation of the new introduced voltage unknown. So we said there are some new unknowns came in apart from the mesh currents at step 2. For this unknown voltage, which are these 3 of them, we are going to use the definition relation of this new introduced voltage unknown, as we said. For example, for this one, we are going to use this independent current source definition relation. For this one, current controlled current source definition relation, voltage controlled current source definition relation. In these definition relations, we are going to see some of the variables which we, which we do not want to see in our equations, independent equations. So we are going to transfer all these unwanted variables with the wanted ones. Wanted ones are those which are mesh currents. So how we are going to do it is going to be seen in the next example. You could understand it better. So, but as a conclusion, what you can say, we introduce some new unknowns. For each unknowns, we are going to write supplementary equations. So our number of unknowns and number of equations are going to be the same. So there is a solution. Once the linear equation is solved, all the mesh currents and new introduced unknowns are found. This solution is unique since the number of equations is equal to the number of unknowns. So once we found all these mesh currents, our aim is to find the analysis, what we understand from the analysis, to find all the elements current and voltages. Now in here we have found mesh currents only. So we are saying, as we explained in 2 framebacks in here, once we found the mesh currents, we can find all the elements currents. The rule is already been set. So once you found the element currents, use the definition relation and find the element voltages. So you're going to understand the whole business here on this example. Here we have a circuit here. In this circuit, what we are saying, we've got 7 elements. So in the classical method, you should write 14 equations and solve these 14 equations. Now we are going to end up here, we are going to solve only 4 equations, which is less than half of the equations that we are going to solve in the classical method. So step by step, let's do it. The first step was this: write Kirchhoff voltage law equations for the meshes. So we got 1, 2, 3 meshes. For these meshes, we are going to write Kirchhoff voltage law equations. For the first one, so VB is independent voltage source. References are the same if you consider the passive sign convention, the current from left to right, and the mesh current is the same direction. Therefore, the sign in front of the B is going to be plus, so plus VB. If you come to the RE, so RE current direction and this mesh current directions are the same, so the voltage is going to be plus sign in front of it, VE. That VE is the voltage of this RE element, RE resistor, let's say. So if we continue to that, so there is a missing again. This is second element, this is R2, then minus this element current direction and the mesh current direction is opposite, so we're going to put a minus sign in front of this voltage, that is minus V2. So we wrote the Kirchhoff voltage law equations for the first mesh. So we have already examined how to write Kirchhoff voltage law equations for a given mesh. We have examples and we have done it in the chapter 3, sorry. So once we have done this, in the second step, what we are doing for the resistors, we are using the definition relation of the resistors and transfer the resistor voltages to resistor currents. Here we are 1, 2, 3, 4, 5, 6. Now if you look at this now, VB here in the first equation is known, isn't it? This is independent voltage source. Voltage, it is a known. So you can write this voltage there as a known. In linear equations, these are the known values. Another known value is that VC, this is independent voltage source voltage, which should be given to you as a function of time. If it is a DC, it's going to be a constant. So that VC, wherever you see it, which is here, you're going to replace this voltage with that value, which is given to you. So VB and VC is known. And what is left here is this element voltage is left here. What is this element? This element is this is. That means current controlled current source. So while we are writing the Kirchhoff voltage law equations, we met the voltage of this element in mesh 3 and in mesh 2, in two places like that. So this element definition relation is here. If you look at this definition relation, in this definition relation, this element voltage is not seen. So I cannot replace this voltage with the current of this element by using the definition relation. So I am going to keep this voltage as it is. So, and then go a bit further. Third step, we are going to replace all the existing currents in this step 2, change all these currents with the mesh currents. So we already seen that, how to write an element current in terms of mesh currents, so we can write all that. So once you wrote all this out that at step 3 level, you see we've got 3 equations and we've got 4 unknowns, not 3. So equations are 3, but unknowns are 4. What are unknowns? EC1, EC2, EC3, and then V, CC, CS. So that means we've got to write an additional equation. How we are going to write this, writing the supplementary equations. This was the element for which we couldn't write the definition relation in this equation, but we know the definition relation of this element is this. If you look at here, as I already said, this dependent sources definition relation is not written next to it. Only the alpha IB is written here. How I am going to transfer this information to this element definition relation is easy. Since you see that diamond shape, that means dependent source. Because of the current reference here, it is a dependent current source. Dependent current source current is equal alpha times IB. So that's the definition relation. So once you write this definition relation, the variables in these definition relations are not among the unknowns in these equations. It's at step 3. So I'm going to transfer these variables to the unknowns seen in step 3. How I am going to do it? Quite easy, because there are current variables here. All this current must be an element current, and I already know that each element currents can be written in terms of the mesh currents, so I'm going to replace these currents with the mesh currents. Rule already been set, so we could apply that. So when you transfer this one, when you write the mesh current instead of these variables, you end up with an equation which includes only the unknowns that I wanted to see in my equation. So 3 equations we already had here, and this last one, the 4th one here, altogether I've got 4 equations and 4 unknowns. Solution of this, you're going to find all the mesh currents, plus you would find this current controlled current source voltage. Then since we have found all the mesh currents here, we can find all the element currents. Once you found all the elements currents, then you can find, by using the definition relations, you can find all the element voltages. That is, to any unknowns have been calculated. So that is the analysis. We have done the analysis through this mesh current method. So in the small video here, when I explained these steps here, I said it only one equation. But in here, you're going to see step by step how these are going to be done. Apart from that, one more explanation. It says here, it is possible to directly write the 3rd step mesh current equations. So although we got 3 steps here, now we are saying that if you think about it, you can directly write a step 3 equations plus the supplementary equations. So think about it and write a rule for you. So that means in practice you can directly write this, but be careful and make a rule yourself and then try to use that. So this method is over here. Come back. So we explained the mesh current method here, and we will be explaining in the next video this node voltages method. So close this.